Dr. Bly's extra credit work sheets. So I'm hoping that they'll still apply in the same ways, I imagine. So the first ones are to give a full curved arrow pushing mechanism for the following reactions. You can use the abbreviated +H+ -H+ notation, but include important resonance contributors for the intermediates and add non-bonding electrons and hydrogen atoms as necessary. I assume that Professor Nedelkova is allowing you guys to use the +H+ -H+ notations. I don't know for sure if you don't know for sure, but I would assume so. But you can always ask. So yeah, so what we have here is we are looking at basically it's a hydrolysis reaction, right? So we're going from, an ester to a carboxylic acid, right? Right, so this is our hydrolysis reaction. So what we need to consider is that this group needs to leave in order for us to add water and OH. And you know, we see this also over here, right? So here's our OET. So in order to do that, first we'll have to do protonate, right? +H+. And with that, because water is a weak base, right? So this is weak base, right? It's a weak Lewis base, so it's not really going to react in any way. So we have to protonate in order to get that reaction to happen. So what we end up having is we have our OET and we have our OH. There's our protonated H. Oxygen. Okay, and then this is when now we have enough energetics to include our water on there. So for resonance contributors here, what we see is our OET and our OH, which now this O has two sets of lone pairs. And then we have these going here so that we have OET and OH, right? So these are all of our resonance contributors, okay? So what'll happen is water comes on. And attacks here. And then what we get out of that is we get water. And we get our OH. Right? So now we need to deprotonate, right? So -H+. Okay, and then we have some stability back in our molecule. OH, OET, OH, right? We're getting closer, but you know, just like OH, OET, they're not good leaving groups, right? So in order to get OET to leave, we have to protonate. So we add OH or add an H. So then what we get, OET, H. Okay. Perfect. And then this becomes a good leaving group. So now this can leave. And then what we end up getting here is we have our OH, OH, and then we have this positive charge here. So for resonance contributors on this one, what we see is OH, whoops. Sometimes the lines don't always come out pretty, right? And then we see the same thing on the other side, essentially, right? H. Oops. Okay, and then all we're doing is just deprotonating. So it doesn't really matter which one you do it on, but oh, let me just draw my brackets here. Doesn't really matter which one you do it on. I'm just going to separate this out a little bit so that we can see. No, wrong one. That's not right. There we go. Separate this out a little bit so we can see that what we're doing here is when we deprotonate minus H plus, all we're doing is pulling these electrons up here, and that's how we end up with our structure. The structure here, right? So we see that, and then our OET came off over here. OETH rather came off over here. Does anybody have any questions about that so far? If not, so then with this one, we're basically just doing the opposite, right? So we're starting with a carboxylic acid and we're ending with an ester, right? So we're just doing it in the opposite direction. And this as well is, right? Because this is an ethyl, right? So ETOH, right? We see that. So that's what we literally exactly what we just did. So we're just going to do it in the opposite direction. And for those of you that have joined, I will try to monitor the chat, but sometimes I don't see it because of the way the screen's set up. So if you have a question, feel free to hop in. Don't be shy. Okay, so same thing with this, right? We have to protonate. So plus H plus, and what we end up with, I'm just going to shorthand this because really you don't have to draw out, this, but this is your phenol group, right? So I'm lazy. So anyway, so we're going to protonate this. So that's what we see here. Okay, and then again, for our resonance structures, what we see is, you just see the same thing on the other side, right? So no surprise there, right? This is just our resonance. Oh, get my brackets over here because I was going to draw it downward. Okay. So anyway, so then what we see is we have our OET. Come on. Right. This is our this base, this acid, right? And then from there, what we have is we see our phenyl group, our OETH positive here, And then we have OH and OH, right? And then so what we'll do is we will deprotonate minus H plus. Again, we're just creating that stability in the structure. These are the long ones that are just like, they're kind of simpler, but they do take a long time because it's a lot of like lone pairs and plus H plus, minus H plus, this, that, the other. So anyway, again, now we have to protonate, right? Because we have to make one of our OHs a good leaving group. So we see this funnel here. We see our OET, our lone pairs. Now we see this essentially water, right? And then, you know, that'll pop off. And then what we see is our group OET, right? Positive here, OH. And then we just have to go through those resonance structures. So again, it's a lot of kind of the same, right? So pH, OH, OET, right? And same thing here. We're gonna get a room. Right? Plus sign. And then what's happening is basically, let's see, I'm just gonna do it in orange so that way we can see this, is where I'm gonna cut through my structure here a little bit. Oh, whoops. Sorry. I cut through my structure this way, I guess. So what's happening is from this structure, we're just doing minus H plus. And so what we see is we see this we see this come off of here. Oh, whoops, not this one. Sorry, y'all. Comes off of this one here. Doop. There we go. All right. We see it come off of there. So I guess we can pull this up here. Anyway. So yeah, you just have to show which structure, which resonance structure it's coming from. So this is that minus H plus here. Perfect. So this is just a reverse reaction of that, right? Does anybody have any questions about that? It's a lot of just that plus H plus, minus H plus, move this hydrogen around, take this off, don't forget your lone pairs, etc., etc., etc. So, and then just recognizing when your, you know, your resonance intermediates are. Okay. And this would be a curved arrow pushing for with our amide hydrolysis. So with this one, we have, we're going from an amide to a carboxylic acid, right? So again, water is a weak base. So we have to do some protonation, right? With this one. Okay, so again, I'm gonna do my funnel here. Actually with your amide, you end up getting this plus H plus, and we see our, let's see, phenyl, this, and H. I don't want to lose any carbons. Right. And then we have our resonance contributors. I will draw them down this time. So hopefully I give myself some space. So remember we have these lone pairs here too, right? So we would see OH. And we would see the other way as well. Positive here. And then what we would see is we would see this. H, OH. Perfect. So those are our resonance contributors, including our positive signs, right? Or formal positive charges. So what we have is we have water attacking. And then we see our phenyl group, OH. Okay. And then from here, oops. From here, we also have a water that's going to deprotonate this. So we'll see this go this way. And then we will see, so we'll end up with, we'll have our kind of more stable OH, pH, and OH. And then over here, we see our NH. And what's going to happen is this is going to take a hydrogen from the H3O plus or an H plus, right? That's really what that means. And this is going to come up here. It's going to leave, which is going to leave us with, oops, hang on, let me move this stuff down. I always end up writing too big. Okay, so it's going to end up leaving us with, now we see, so this little piece here, this came off, right? And I'm pointing that out because we have it up here, right? And it'll collect, because it's in an acid condition, it'll collect another hydrogen, and that's why we see a third hydrogen on here. It protonates. But this is where it pops off anyway. So that's why you see that. And then from here, so now we just basically need to get our carboxylic acid, right? So we have pH and we have OH, and we have a positive here and an OH here. And then we just have that resonance structure. So, and it's, you know, basically the same, but flip-flopped, right? OH positive. Then we also have this pH, OH positive. Okay, so those are our resonance structures here. And then what we see is, whoops, this one. It's water coming in, right? It's just minus H plus, right? But water coming, oops, wrong way. Water coming in, taking this hydrogen off of there, and that's how we get this. So deprotonates it, right? So the water, the plus H plus, minus H plus, right? Like you can do it, you know, either way, but just to see it kind of a few different ways. So that's amide hydrolysis. I mean, pretty much the same, a little bit different, but kind of the same, right? So any questions about this?
Not so much about the problem, but could you go over what like amine, amide, and I feel like there was another one. It's not about the like first degree, second degree. Like, why do the amide names change again?
Yeah, so the best way that, so an amine would be like, sorry, I'm just trying to change colors. So this would be an amine versus this is an amide. And the best way that, like, my little trick to remember which one is which, because it can get confusing, and then you, of course, you have a nitrile, which is, this, right? But the best way that I have been able to remember what the difference between an amine and an amide is by how it's spelled. So to me, with this D here, it reminds me that there is an O connected. There's an oxygen. See how we have this in this example? I'll use this example, right? So R, right? So an amide has this double bond O connected directly, or not directly, but very closely connected, right? We just have this one carbon between it, versus an amine, and amine, excuse me, is just, whatever, third degree, second degree, right? And I'll cover that too, but no oxygen, right? So there's no oxygen that's, 2 scores away, right? So that's the best way that I like this D here kind of reminds me of, like, double bond O, right? It's silly, but it's just the way I remember the difference. So, and then the difference between, like, first degree, second degree, amines is if you have versus this is a first degree, this is a second degree, or primary, secondary, right? Tertiary would be with 3 R groups on it. So R is just any, hydrocarbon chain, right? And so first degree just means how many hydrocarbon chains is connected to it. So this one has 1 hydrocarbon chain. This one has 2 hydrocarbon chains. That's why it's second degree. This one has 3 hydrocarbon chains. This would be tertiary or third degree. Amine, right? So it just has to do with that. So this one would be a primary amine because it has 1 hydrocarbon chain on it. Does that make sense?
Yeah, that helps out a lot. Thanks.
Yeah, no problem. Yeah, no, I know. Honestly, it took me a long time to kind of figure out, like, what the heck is the difference between an amine and an amide. And I did everything like ChatGPT, asked professors, and, like, it was just like I went down the rabbit hole and it just got more confusing the more I read. And then I realized one day that there was a double bond O and it reminded me of the D, because, so anyway, hopefully that trick helps you.
Thank you so much.
Yeah, no problem, no problem. Any other questions about any of this stuff? If not, we'll keep it trucking. Okay, so this is just provide the missing major organic products or reagent conditions or organic reactions, right? Reactants, as appropriate. Don't forget to include stereochemistry as appropriate unless specified otherwise. I don't really think there's a lot of stereochemistry in these anyway. So, so the biggest hint on a lot of these, the biggest hint on a lot of these is that all acid derivatives hydrolysis reactions, right, will give you a carboxylic acid. So, so this is a hydrolysis reaction, right? So we're going to break it, here to get our carboxylic acid, right? So this will protonate out because it's in an acid solution. So it's just like before, how I had mentioned up here, that the reason why we see this extra H that we don't see here, right? We have 1, 2 here, and we get this third one here because it's in an acidic condition. So same thing with this, right? It's in an acidic condition, HCl. And then we just have, so we're just basically copying the structure down, right? And then we just have this, it is one away, and then we have our carboxylic acid, right? So nothing crazy happening there. Right, anhydrides. With this next one, same thing, right? Or H3O plus, right? So we're gonna see the same thing. But this time we're gonna see what? We're gonna see two of them, right? So we'll have two carboxylic acids. So we will have our first one. And then we'll just have our one, right? And then so we see here from our H2O, right? H2O, oops, is we have, let me put this here, oops. Our OH comes from here. And our H comes from here, right? So that's where this is coming from. So same jam, right? For this next one, right? So same jam. We're seeing this. Just draw out your structure. I guess you didn't have to put the C, but I did for consistency's sake, right? And then same thing here, OH, right? So we just see that happening pretty much over and over again in a lot of these reactions. For this one here, so a good way to think about this is that we have, when we have these reactions, we have some sort of OH, right? Some sort of alcohol, so ROH, right? And then we have some sort of, in this case, plus chlorine. Sure. Right, but we could also just say, if we wanted to, we could just say anything here, right? It doesn't have to be this exact, but just say anything here, right? And so what we're doing is this is what's leaving, right? And so we just have to connect the dots. We just have to connect the two. So then this then becomes R O C double bond O R, right? Oops. Right, so that's what we end up getting. We could do R prime if we wanted to show that it was something different, right? So yeah, so with this, we just see that same thing here. We have our phenyl group. Sometimes it's easier just to draw the bigger structures first. And then we have O, and then C, double bond O, right? So here's our three from here. 1, 2, 3, right? That's all we're doing. We just got rid of this H and this Cl. We made those new bonds. Okay. So what do we got here? So again, this is kind of similar in the sense where, you know, so we're moving into this adding of the amines, the amides, we're creating those amides, right? So like from before we did it, I guess we did the reaction the opposite. We had the amide and then we got the carboxylic acid. So, but that's what we're doing here. We're going from the carboxylic acid to this amide, right? So, remember this is just CH3 here, right? So what did we do here, right? So all we did was we turned this OH into this, you know, amide, but you know, we added the amine and the CH3, the methyl group, right? So, but the problem is that OH isn't a good leaving group, right? So we have to do something with that. So how do we, and this was like in the beginning, right? In the beginning of the chapters here, we have to do something to that OH group in order to turn it into something else, right? Does anybody remember what like one of like the first reactions are that we did in this chapter or this section? We have to turn it into a chloride, right? So you turn your carboxylic acid into a chloride, and then you can you can use that to make any kind of derivative that you want, right? So if we do, whoops. So we do our SOCl2, and then we just add this, becomes our Cl, right? And then we just add whatever it is we're trying to put on here. So what we're trying to put on here is our NH2Cl or CH3, sorry. Obviously, you have to add an extra hydrogen on here for it to do the reaction, right? So that's all that's happening. Same thing here, right? So we added that extra hydrogen for this reason here, so that we can cut out our Cl with the hydrogen, and then we just add on whatever's attached to it. So the second part of your reaction is just whatever you want to attach to it, plus an H, right? So with this, what are we doing? This is also acid synthesis, right? We have Br. Does anybody remember where the bromines would go? What kind of bromination is this? Does anybody remember? There's a few different brominations that we had. We had Br2, which would add it to our alkenes. Right? Br2 with H nu, and that was that radical bromination, right? And then this other one that we're seeing here, Br2 FeBr3. Does anybody remember where those get added on to? The benzene ring, right? We see it in the aromatic benzene rings. A tick, right? So where would they go on the benzene ring though? Because there's a lot of options, right? What is that? What's this ethyl? What is it going to do? Is it a donating group or withdrawing group? Anybody remember? It's a donating group, right? It's not going to withdraw any of its electrons anywhere. It doesn't have a more electronegative atom that's further away, right? If this was OH, then this would be a withdrawing group, right? Because the oxygen is gonna pull the electrons towards itself, but it's not. It's just a methyl at the two methyls, right? It's an ethyl, but off of this carbon, it's just a methyl. So that makes it a donating group, right? So where do donating groups direct? If you're adding something with a donating group on your benzene ring, where do they go? Ortho, meta, para. Anybody? It's lonely out here. Ortho, para, right? Ortho or para. So we add a BR in one of these spots, right? But, for this purpose, you have to show both, right? And it doesn't matter because these two are the same, right? So I'm only going to draw one of them. So you add the BR, then what happens? This is a Grignard reagent, right? We have the Mg THF, so then this becomes MgBr The short story is that Mg is inserted between the carbon and the Br, but really there's like this whole mechanism that happens you don't have to worry about, where this gets pulled off and then that gets put back on and all this other crazy stuff, right? But anyway, we don't have to worry about that. And then what are we doing? We're carboxylic acid, right? So we basically are just drawing the structure with two different carboxylic acids, right? Not on the same structure, on two different structures, right? So what we have is we have a, whoopsies, a phenyl group here with our carboxylic acid, and then plus we have a phenyl group here with our carboxylic acid. Sorry. I know it doesn't really look accurate, you know. The geometry isn't great, but hopefully you guys understand. Yeah. So let's see, what do we have next here? So one equivalent, right? Does everybody see that? One equivalent. What are we doing? What are we doing with this? So we talked about this, right? We talked about this up here. We talked about this right here, actually, right? And same thing here, right? So all we're doing is just, we have a hydrogen either here or here or here, right? Because it's one equivalent. I mean, we're only going to do it one time. We're only going to make one reaction. So which of these three do you think would be the best, or the most likely, I guess I should say, to have this reaction, right? A, B, or C. Let's not forget our lone pairs here, right? Anybody, take a wild guess.
Oh,
C.
C, yeah, why?
I would have to look at my notes, but just that was my wild guess. Sorry.
No, that's good, that's good. I'm glad. Yeah, go ahead, hop in.
I think it's because it's on the least substituted deal there. That's not.
I think I know
Yeah.
where you're trying to go with this. So it's not that it's the least substituted, because they're all NH2, right? But it has the least resonance happening with it, right? Like A and B are going to be busy with resonance, because this is going to come here, this is going to go here, this is going to go here, right? These are going to go here, right? So their electrons are going to be more busy with resonance, versus this one, there's nowhere for the electrons to go, because if we remember, these are some hidden hydrogens here, right? So this is an sp2 hybridized carbon, sp3, excuse me, hybridized carbon. So that one's not going to go anywhere. So the most likely, or, you know, yeah, the most likely one equivalent, right, is going to be on C. Yeah, great guesses. And so then, of course, it's a pain in the booty to draw out, but that's okay. Yeah, I'm just going to do this. And H2. And, oh, don't miss that. NH, and then we just add this on, right? So we just add essentially this on, right? To here. Cool. Yeah. Okay, so Sam Jim, what are we doing? What does this do? It's another bromination reaction. Where does it go?
At the end of the double bond.
Yeah, exactly. At the end of the alkene. Yeah. So we would have a bromine here, right? And we would not have this alkene, right? So we'd have that bromine there, and then what? Here, I'll draw it out for you guys. Right, so we would see this. Right. And then what? Then we have NaC, well, nitrile, right? Where's that gonna go? What happens here?
It's gonna replace the bromine with C double bond, or sorry, C triple bond end.
Yeah, exactly.
Yeah.
Yep, exactly. Then what? Just gonna protonate a bunch of stuff, right? Essentially. Right? So we're just gonna see CH2, whoops, NH2, right? So we're just gonna, this is 3 and 4, right? 1, 2, 3, and 4, right? So we're just gonna protonate a bunch of stuff. So that's what we see there. Yeah. See, not bad, right? What about this next one? I'm gonna do it in different colors so we don't get mixed up. What happens here with this next one?
It's going for the first step, it's going to make the primary alcohol into carboxylic acid.
Nice job. Yep. And then what?
And then the OH will turn into a Cl, but I don't know about the Py. Or...
Yeah, it's just like a catalyst or something. It's not important in your
version.
Yeah. And I literally wrote, because we were talking about OH, I literally wrote OH again. Okay, anyway. And then what? Now we have excess MGBR. So what's that mean? Right, the
Would it
excess is what's
replace
important.
would it replace the Cl?
Yes, it will replace the Cl. First, we'll see the first time we will see, well, really what we're doing is we're adding a CH3 here, right? Because what's happening is the MGBR is coming in and attacking here, and H is coming off, right? With this Cl. The Cl is leaving. It's, getting an H somewhere, right? And this MGBR is coming in and adding our CH3, right? But because this is excess, we're just going to see it happen twice, right? So it's that same idea where, if you have it just one time versus you have it multiple times. So what we end up having is the reaction will continue, and then we'll just see it all the way through. So CH, because this is really what we're adding. We're adding that CH3. The MGBR goes off in place. And then we have this, our acid workup step, which you need at the end of every Grignard reagent, right? So what we're seeing, and we're gonna see it again with this next one here. What we see is, this is like a little pattern and tip, is, I'm gonna pick a color that I haven't done yet. Okay, so anything where it's like this or an ester, right? Anytime you add whatever our X is just a halide, right? But in this case, typically we use Br, right? This is an excess, right? And then our acid workup step, right? You're gonna come out with R, C, OH, and then just whatever your R's are. So you're gonna see this. Let me just write excess here, right? So it's just gonna do the reaction twice essentially, and then it's just gonna add whatever this R group is that's with it. It's just gonna add that on twice. So you'll see it both with your chlorine or an ester, right? But if you have this C double bond O, it's just gonna continue and proceed. And so with that being said, right? What do we see next, right? We see an ester. So what happens here? So we're gonna cut that there. And then what we see is because we have like this excess again, so this means that it can happen as many times as the molecule will possibly let it, right? We have, let me just draw the structure as it is so we can see this. Okay, and then what we're seeing is we have, again, we're just this, let me make sure my colors are different. So this is going to get, why is this working? A hydrogen from here, or H3O plus, right? And this is getting a hydrogen, let me use a different color again. And this is getting the hydrogen from here. So we're breaking that up, turning them into alcohols. And if you wanted to make it pretty, as they say, right, we could do HO and then 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then this is 1, 2, 3. Right? 1, 2, 3. Yeah. You could also draw it like that. Right. So anytime it's the excess is when it's just going to go until it can't go anymore. But in this case, we're just protonating, right? So with these, so indicate which compound will have the highest and lowest Bronsted acidity. So a stronger acid has the strongest withdrawing group, right? So it needs to be stabilized. So what we're looking at here is we want to see which of our acids, because if we, let's see, let's just like negate this, right? But if we're just talking about this top half here, right? So our acid is going to be this CO and then O, right? Because we've deprotonated it, right? So we want to know which one is going to be our strongest acid, right? So our conjugate base is going to be stabilized with a strong withdrawing group, right? Because anytime we have a withdrawing group, it's pulling those electrons towards itself. Okay, and then so what we're comparing here is the withdrawing groups that we have, right? So we need to decide which one is going to be the strongest withdrawing group, right? So the highest and lowest Bronsted acidity. So what do you guys think of A, B, and C? Which one has the strongest? Or even start with this, which ones are donating and which ones are withdrawing?
Is C withdrawing?
Yeah, C is the withdrawing group, right? The best way that I have to explain as like a shortcut of withdrawing group versus donating group, obviously there are some exceptions to this rule and I'll explain that, but is if your you have an atom, let's say in the first position from the benzo, from your ring, right? And then you have another atom that's in the, say, second position, right? And so if the atom that's in the first position is more electronegative than the atom that's in the second position away from the ring, then it's going to be a donating group. Whereas if you have an atom where the second positioned atom is more electronegative than the first position atom, then you are going to have a withdrawing group because it's more electronegative. It's going to want to pull those electrons towards itself. And in this case, not only that, we also have this negative charge here. Or is that, yeah, negative charge here. So we have this withdrawing group here. Okay, so then the exception to the rule would be, well, if this was negative, whoops, sorry, let's just, let's say this C was negative for whatever reason or whatever, then this negative would obviously be a stronger withdrawing group, or I'm sorry, positive. It would be a stronger withdrawing group because these electrons would be going towards this, right? And so this has both. This has both a positive charge there. So anyway, so that's the kind of the short and sweet version. So if your second positioned atom is more electronegative than the first position atom, it's going to be a withdrawing group because it's going to be pulling the electrons towards itself. So this is the withdrawing group. What about A or B? Withdrawing group, donating group. Well, this is just a methyl, so this has got to be a donating group, right? It's not going to pull anything away from it. Resonance structure is going to just pull its atoms with it. And what about B?
Is B a donating group?
Yeah, B is also a donating group. Cool. Which one? So we know that C is going to be the strongest, right? But what is the highest Bronsted acidity, I should say, strongest acid? But which of these two, A or B, like which one's the stronger donating group?
B.
Yeah. Because we've got lone pairs we can donate to, right? We've got that resonance. So B is a stronger donating group, so it's going to be the weakest because it's going to give, again, remember that in order to stabilize our conjugate base, we need to have a withdrawing group. So if it's a stronger donating group, then that means it's least stabilized, right? Does that make sense? I know sometimes that can get a little confusing. So that's what we see here. Oops. Cool. So then with this, rank A, B, C in order of increasing basicity. So what this is asking is which nitrogen will pick up a hydrogen? What do you guys think?
Would C be the one that is most likely to pick up a hydrogen?
Yeah, so it's got the strongest basicity, right? So C is the strongest. Why?
Because on A and B, there's the oxygens with the double bond, which could donate to the nitrogen, whereas C doesn't. I don't know if that is an actual logical reason, but that's how it goes in my head.
You're close. Does have to do with the oxygen, but notice how every structure has a O double bond to it, to this pentane ring.
Yeah, it does, but in A and B, it's in the primary carbon from the nitrogen.
So what does that do? Why is that important? You're almost there. I know you know what this is, but it's just the word. What is it that this is doing?
Is it resonance? Yeah.
Yeah, it's resonance. Exactly. Exactly. Right? So we've got resonance here. But on B, we see we've got two places of resonance versus we only have one on A, right?
Yeah.
Yeah. So that's why B is the least, right? Weakest, because we have more resonance, right? Yeah, nice job. I know sometimes the wording you're like, what? It just because I know that that's how it works. I don't know why. It's just like what I've learned, right? So I get
Yeah.
it, you know. Okay, so show how you would. Does anybody have any questions so far? Hopefully, I haven't like skipped over anybody. I haven't seen anything. So,
Yeah, sorry, I've
um,
kind of been yapping.
no, please. I prefer for people to like engage because it's like, otherwise I'm just like kind of going through it. And it's like,
Yeah.
anyway. So show how you would synthesize the target compounds on the right from the starting compounds on the left. Show your reagents and conditions and the structures of important intermediate compounds. Don't show any arrow pushing mechanisms. Right? So that's always nice. So what are we doing here? So we have an amine. How do we make amides?
Um, would the step before be well, I'll do what would be on the arrow is like the reagent. NH2CH3 or
Exactly.
yeah,
Yeah,
yeah.
that's how we add this, right?
Mhm. And
So you go ahead.
the a Cl is replaced with the NHCH3.
Yeah, exactly. Yep. Yep. And then how do we get that CL on there?
Um, the reagent I believe is SOCl2.
Yeah, exactly. Yep,
And that came from a carboxylic acid.
exactly. And this, my friends, is pretty much what you're going to see anytime you want to, like, you're going to go from a carboxylic, COO2. Oh boy. CO2H. Anytime you want to go from a carboxylic acid to some type of derivative, right? Acid derivative, you're gonna do this mechanism here, right? Like this is gonna be pretty much your go-to. This and then whatever you're adding on, right? But this whole situation here. Yeah, perfect. So then now if we look at the structure, we've gone from we have obviously our phenyl ring here, right? And then we have 1, 2, 3, right? We have this isoprop on the ring. And then what do we have over here? So from this structure, we have 1, 2, 3, and we have this carboxylic acid that's been added to that structure, right? So that means that we have this other carbon. So there's a couple ways in which you can go about. Remember, there's a hidden hydrogen here, right? There's a couple ways that you can add a carbon to your structure, right? Those carbon-carbon bonds. Does anybody remember?
Is it it comes from an MGBR.
Yep,
Um
that's one way.
and I think the step is CO2H3O,
Yes.
like as step 1 and step 2.
Yeah, so yeah, MgTHF. I mean, I guess you would. Yes. Because let's see, CO2, H3O. I could like do this out, but I want to be able to show you both steps. So I'm only going to do it in just a one step situation. But, from this, it would be, yes, you would have your whatever this is, right? And we'll talk about that in a second, right? And then you would have your CO2. And then this would be this next step, but we're just gonna add them all together to get this, because we know that we can extrapolate that, right? So this is one way, yes, your Grignard reagent, right? Oops. Grignard is a way that we can make carbon-carbon bonds. What's the other way that we know how to make carbon-carbon bonds?
I don't know the exact name of it, but
I know I just heard it
would
too.
you would you start out from the beginning structure? Would you use that like KMnO4 and then like under OH and boil and then
Yeah, good.
O plus, and that makes the carboxylic acid.
It does make a carboxylic acid, you're right. But what it does, no, it's good. This is good, right? So let me just kind of scroll down here where I have some space, right? No, this is good. I'm glad you said that. So when we have some sort of, right, structure here, and we add, like you said, that KMnO4 OH minus, and then we have to do our acid workup step, right? We get a carboxylic acid. You're absolutely right. Because we are oxidating. This is an oxidative reaction, right? We're making more bonds to oxygens. So here's the thing. What we've done is we've made this carbon, whoops, and now carboxylic acid. Now, here's the other one that I believe, McKenna, maybe was it you that was?
With the Grignard?
Yeah, with the Grignard, yeah.
Yeah.
So if we do a Grignard, now what we have.
Is it because we didn't add another C to the
Because we didn't add another carbon, right? And so this was what she was saying, CO2, H3O plus, whoops, 3O plus, right? So now we've made that carbon-carbon bond, right? That's what's important here. You need, as you're doing synthesis, you need to decide, am I creating another carbon-carbon bond, or am I just turning this into a carboxylic acid? Because if you're just turning that primary acid or primary alcohol into a carboxylic acid, then yes, absolutely, KMnO4OH, right? And then your acid workup step. Yes, 100%. But if you want to add another carbon, right, because this is that same carbon and here's that same carbon, if you want to add another carbon there, there's one of two ways, right? So Grignard is one. Does anybody remember the other one?
Is it the NaOH is the next step, or
The close Na. What's this part? What's this next part?
CN.
Yeah, CN. Yeah, exactly. Yep. So they'll both work, right? And then you would have RH2, CN. Then you do an acid workup step, H3O plus. And then you would end up with same thing, same. Oops. So those are our two. I'm gonna do this. There we go. Those are our two methods, right? So we have the acetylide, is that what it's called? And then our Grignard, if we want to add a carbon, or KMnO4, if we're just trying to turn that primary alcohol into a carboxylic acid. So coming back to here, are we adding a carbon? We decided yes, right? We see this blue carbon over here. Oops, we see this blue carbon over here. So one of two ways, we can do this MgTHF, right, our Grignard reagent, or we can go back and we can do the same thing with our acetylide, or I'm gonna butcher it, but NaCN and H3O plus, right? Both of them will give us that. So what is it that we need to work with this though? what does this need to turn into? What does our primary or original structure need to turn into in order for us to add that? What are we doing?
Do we have to do NVS in light?
Yeah, you could do it. Yep, you have to add a bromine, basically, essentially,
Yeah.
right? And so we have to add a bromine here because this is where so we know for sure that we don't want to do the BR2 FeBr3, right? We don't want to do that because it'll add it to our benzene ring, right? So we're not doing that. So we can either do NVS HNU, or we could do BR2 HNU. Either one in this case would be correct. And then we get that benzene, that bromine on there. And then we either proceed with option A or option B, right? And both are equally correct, and we'll give you this same product here. Okay. Any questions on that? Great job, you guys. Good stuff. Good stuff. Okay, so same thing here. So what are we doing? Obviously, we're just starting with a cyclohexane, and we've now added this whole ester function, ester group over here. So, so what do we have to do? We can start from the back like we did last time, right? They would say retrosynthesis, although I'm not a fan necessarily, but in order to get this on here, it's the same thing, right? We've done this before. We've done this before over here, right? Our two in purple. So what do we have to do? If this was a carboxylic acid, right? We need to add this. Which would, right? We've done this before. We just did it. We saw it. And we do the same thing again. SO, Cl2. Okay, so we've grown our chain. So we started with well, we ended with, I guess you could say, our ester group. We grew our chain, and we had to do that by, remember, where this Cl and this H are going away so that we can create this new bond, this new group here between this and this, right? That's what we see here, and we see here, right? So that's all we did. And we had the Cl in here, and in order to get that Cl on there, we, from a carboxylic acid, just did SOCl2, right? So now once we're here, how do we get a carboxylic acid onto cyclohexane?
Either from the Grignard or the NaCN and then H3O plus.
Yeah, exactly. So what do we have to do? How are we going to get a bromine on there? How are we going to make it a bromide? Right. BR2HNO, right?
Does NVS in light still work for that, or would it be preferred to do BR2 and HV? Because I know that I forget which ones, but certain ones it doesn't work.
Yeah, I think NBS and HNU are the ones where it's like that is compatible with everything.
Yeah.
If I'm remembering it correctly, and BR2 HNU
is more selective.
Yeah, that's more specific. So it's always, I have always been told, like, just do the one that works for everything, and then you don't have to remember the specifics. So much so that I don't exactly remember the specifics off the top of my head right now. But yes, it's always safer just to to do it that way. I would agree with that. And then so same thing as before, right? So we can either and I'll do them in two different colors, right? We can either do MgTHF and then CO2 and then H3O plus, right? And that will get us this. Or we can do NaCN, which will replace our bromine, and then our acid workup set. I don't know if she'll let you just combine and do 1 and 2 and just go directly. I don't know. You know, does she let you guys do that? I'm not sure.
Well, it's going to be different. Yeah, it's going to be different since this time it's going to be all multiple choice or like choosing the box instead of written.
Got it. Oh, you guys don't
So
have any written
not for this
for
one.
this
The other
final?
exams we have, but for the final,
Yeah.
it's all multiple choice.
Oh my gosh, you guys are lucky. Jeez. You guys lucked out in a lot of ways in this class. I'm like, gosh, I should have taken her class.
Right.
No, that's good. That's good. That's nice. Okay, so you don't have to worry about it then. Whatever she has there, you just select it as long as you know what you're doing.
Yeah.
Okay, so last one. This is the last piece that I have here. So with these synthesis, right? So this is one that's a little bit more, it's going to ask you to think about things from before. So what are we doing here? What's the difference between the structure, right? So what we've added is this here, right? So basically all of this stuff here is what we've added. Okay. This and this is the same thing. Okay. So what do we do here? The amide has to come from an acid derivative, right? So we've been doing that. So what are we adding? How
Would
is
it
the
be,
amide? Yeah, go.
sorry, would
No,
it
no.
be NH and then in parentheses a CH3 and then a 2? Like to show that there's
Yeah,
2 CH3s?
yeah. Or you could do it like this too. But yes,
Okay,
exactly.
yeah, okay.
Yep, either way. Or what you were saying is NH, CH3, and then 2. All right, so either way is fine. Either way is fine. Yes, perfect. And then so what we have then is our, how do we get that on there? We need the,
There a
what would be,
chlorine on that one.
yeah, exactly. Okay, and then how do we get that on there?
It's from a carboxylic acid, so it would come from SOCl3,
Yep.
Cl2, sorry.
Yeah, no, it's all good. All good. Let me see, I don't lose my carbons. Ugh. Right? Okay, so now what? Ooh, now what?
The Grignard reagent or NaCN and H3O positive. Is it the same with this
Yeah,
one?
yeah, but think about what, so if we just put a Grignard in here, wouldn't we see it reacting there as well? Wouldn't we see the Grignard react here as well?
Yeah.
And we would also see the acetylide or whatever, the nitrile would also, right? Because we have a Lewis acid here, right?
Yeah.
We have that positive charge there. So what is it that we had to do to
Would
get
it
it to
have,
only react? Yeah.
oh, sorry.
No.
Would it have to come from an alcohol?
What do you mean?
Like, from a primary alcohol and then doing Na2Cr2O7 to create the carboxylic acid.
Um, so what you're saying, turn what into an alcohol though?
Turn like where the carboxylic acid was added into an alcohol.
So turn that into an alcohol. Okay, so if we did that, right? So then we would just have, oh, whoops, no, sorry. Well, if you turned this whole structure, whoops, if you turned this whole structure into just an alcohol, then what you would have is you would have OH here, and then you would have your phenyl group, right? So, but how would you get this? Oh, I see what you're saying. So you would do this and then do the,
Yeah.
okay, you're like, this would be before this. Got it.
Yeah.
Okay. I get what you're saying. I thought you were saying like, go
Oh
back
no,
a step.
sorry.
Yeah,
No.
no, it's okay, it's okay. That's what I was like, how would you do that? Okay, so then what you would have is you would have OH, and then you would have this, and then you would have this. Okay, and then what would you do?
For the reagent to get the carboxylic acid,
No, we know
or
this
just the
part.
step
I'd say, yeah, how would you put the
Okay.
alcohol on there?
Is it that PCC thing? Like,
Yeah.
or no?
Well, because you have this methyl already, you have this CH here.
Yeah.
I can't think of a way that you can add an alcohol to that. What is it instead? When we had, remember, aldehydes are more or ketones, aldehydes. What was it that we did that last chapter to prevent them from reacting in our Grignard reagents?
Oh, we took like that double bond, and we did that. Where we did that like, HO, and it had like that connection thing.
Yeah, we put a protector.
Oh, wait,
Yeah, we
and
protected
HCl.
it. Yeah, exactly.
Oh
Yeah.
yeah.
Yeah. Much simpler, right? Than trying to like come
Yeah.
up with all these like crazy stuff, right? No, I know it's hard, like especially this synthesis stuff. It's like kind of crazy, right? And so then we need, of course, our catalyst, right? So we just protect our ketone, right? So then we have this. Now that our ketone is protected, now what? Now we can do what we want to do, right? So what do we want to do? Right, we want to add a bromine. Where do we want to add the bromine?
Into the methyl group.
Yeah, exactly. Sorry, my drawings are coming together. Yeah, we want to add a bromine to the methyl group. Exactly. And how do we do that? NBF, yeah, HNO, yeah. We're just not going to use that Br2, Fe, Br3 or whatever, because that's going to add it right to the benzene. Right? Yeah, so we do that. And then what? Let's see, where are we at now? So now we want to turn that bromine into a carboxylic acid. What do we have to do?
Ben, can you do the Grignard reaction?
Yeah, you could do Grignard, or you could do the NaCN, right? Either way.
Yeah. So the step that I missed was the protection. Okay,
Yeah,
that makes sense.
yeah, right. It's tricky. It's tricky. So let's just say we do the NaCN because we're gonna do this. We've got our phenyl group, and then we've got There's CN there. And then when we do our H3O plus, it's just going to get rid of everything, right?
Yeah.
So it's going to give us all of that back. So it's going to get rid of the protecting group, and it's going to give us that carboxylic acid on the end. Right?
Mhm.
So yeah, so tricky, right? So remember that when you have those, you know, in this case, this is like this will react with a nucleophile, right? A nucleophile will come in and it will react with this place here. And so if we want to add something here, but we don't want to add it here, because remember this still on this side, whoops, right? We still have that. So yeah, so that's why we learned that in our last period, so last section. So that's all I've got. What do you guys think? You got any questions about anything? You guys are lucky you got drop down menus. That's pretty cool.
I know. It's weird though. I feel based on my grades, I've been doing better on the written parts, which is typically not the case for me. So I'm kind of nervous for it.
Oh no.
I think I
Oh
just
no.
overthink the
Yeah,
answers.
totally. Especially when the answers are like, it's like one lone pair off and you're like sweating about it. Like, oh crap, which one is it? You know,
Right. Yeah.
it's the worst. I know it. Yeah, just my suggestion with that is just I don't know if this is what you do, but every time I take an exam, I will go through it. And then I go back. Once my exam's done, I typically have time left over. This only works if you have some time left over, because otherwise the anxiety gets worse. But if you have time left over, it's just to go back over every single question, not like, oh yeah, no, I got that one, but actually just reading it through thoroughly and making sure that you didn't miss something or like forget about some resident structure or something. So because sometimes too there's clues in previous questions that will help you kind of jog the memory and stuff. So
Yeah.
if you're not doing that yet, I would definitely suggest just going back through and looking at everything. And sometimes when you second guess yourself, usually it's your first guess that's right. So, but yeah, well, congrats to you guys for making it through.
Thank you.
Yeah,
Appreciate your help.
absolutely. Yeah, no problem. Let me know